Hi, in this session we're going to cover masonry movement joints. My name is Sam Rubenzer. I'm the founder of Force and the managing director. I'm a licensed structural engineer in the state of Illinois, professional engineer in several Midwest states. Got my engineering degree from University of Minnesota and an MBA from Marquette University. So in this session we're going to cover some movement joint and a control joint definitions, cover some different horizontal reinforcement options, and then really try to create an understanding between control joints, movement joints, and different reinforcement options. And then we're going to look at some design impacts of the various options. So in the what's in masonry materials, obviously we have the block, mortar, grout, vertical reinforcement. For today's session, though, we're really going to cover the horizontal reinforcement and control joints. So control joints, horizontal reinforcement, do masonry walls require control joints? If control joints are provided, then what type and how much reinforcement is needed? And if control joints are not provided, then what type and how much reinforcement is needed? So some of the different questions we're going to try to answer on today's session. So how much horizontal reinforcement with and without control joints are all things that are going to be very um, important to be able to address. But if we look at those two different options, obviously the contractors that look at these two different options are really going to look at cost implications and constructability. Really, the architect's going to, also want to weigh in, how does it look? Is this going to crack? Is this going to be causing problems in the future? Stuff that we'll have to address. And then obviously the engineers looking at who designs in certain areas without control joints. It's certainly different parties all have different perspectives on these different options. So just a really quick review. Um, when you have buildings, all buildings are going to move. Temperature loading. Temperature loading is really just a change in temperature. As we change temperature, obviously the materials that we build with have some expansion or contraction that they're going to see. If there's a temperature increase, obviously an expansion. If there's a temperature decrease, a contraction. Sometimes in some areas we have some pretty big temperature swings. So those can certainly add different loading. Buildings move also though just due to the typical just building loads, whether or not they be gravity loads that are acting on a structure or lateral loads that are going to be acting on a structure. So all different things that really cause materials to want to move. Then you have some chemical reactions with concrete masonry. You have dry shrinkage. You have the material over time that's going to want to shrink in size, and that has different effects on an overall wall system. Or you have clay masonry that actually is going to take on moisture, and actually the material is going to grow over time, hence the expansion. So really our two different options are to accommodate that movement by using joints in select locations, or restrain that movement, or sometimes a combination of the two, um, to resist some of the movement. Some of the different guides that we're going to use today come from the CMHA, Concrete Masonry and Hardscapes Association. So the guide that we're going to mainly reference is the CMU Tech 9-25, which is really a compilation of several different NCMA tech guide materials that we've referenced through the years. And so using these different guides, we really come up with three main options for movement joints and horizontal reinforcement. So really the first option is probably the most prevalent option, is to use some horizontal joint reinforcements or minimum reinforcement and regularly spaced control joints. Most common, most people are very familiar with that option. Option number two, we'll be looking at um, really using bond beams to restrict that movement. So bond beams with reinforcement and minimal to no control joints in our designs. And then option three would be kind of a combination of joint reinforcement and bond beams with, again, that minimal or no control joints that we're looking to achieve. Really, kind of the first thing that we should think about, though, is who's responsible. Looking at the checklist that we have within the TMS code, it actually indicates that the designers, architects, engineers are required to indicate the type and locate the locations of the movement joints, so control joints, expansion joints, so on and so forth, on the actual drawings. So a lot of times, if I was looking at an architectural set, I would be typically looking for expansion joints, say a veneer. But I would say in today's world where we're delivering a lot of digital documents, it's also then a really good idea to also put an elevation out there for the concrete masonry elements in an elevation so that we can see where the joints should be in that elevation. Now, sometimes they're going to be in the different locations than the veneer, and that's certainly very much okay. In fact, that would be somewhat preferred. So, I think having the two different elevations would be a very good way to show the differences between the two. So, again, what are some of the different definitions here? We have movement joints that can either be control joints or CJs, commonly used for concrete masonry, and then you have expansion joints, typically listed as EJs on drawings, which are going to be commonly used for clay masonry. So, really, you could use CJs, EJs, or just MJs, movement joints, for both. You really have different options. And I see all across the country in different offices, we see people have their different nomenclatures that they use. I would say the biggest thing is just try to be consistent through all of your drawings and documents, and certainly within the design team that you're working with. So I said before, the CJs and EJs don't need to align. In fact, that they shouldn't align. If you think about the joints, are really going to be kind of weaknesses in the overall wall systems in terms of water penetration or different things getting through into the building. So there really wouldn't be a good reason to align the joints. In previous construction, we had composite walls. With composite walls, you really wanted to have both the joints aligning together, but we don't use this type of construction anymore. Really, once we understood and we saw some of the behavior and how, putting both, say, clay materials and concrete materials compositely together, you could see one's trying to expand, one's trying to contract. There's going to be cracks in one or both ways. So we don't have these composite walls. In fact, if we were rebuilding a wall that was a composite wall, we're going to really try to steer the construction to be a cavity wall, not a composite wall. So if we don't have these, then there really isn't a need or want to have these joints align. So with a cavity wall type of construction, having those joints really kind of being there for different purposes, and we'll talk about why a veneer joint, usually an unreinforced veneer, typically has very different locations that we would want to locate the expansion joints within. So in the backup wall, we typically have reinforced walls, which would have a very different set of criteria for locating those joints. So they're generally not going to be in the same location. We wouldn't really want them to be anyway. Another little tip for construction is certainly if you're looking at the width of the joints, you're going to see some differences here as well. Where again, the control joint, 3/8 inch wide, just the standard kind of gap that you would have for a mortar joint. We're going to be able to use that for CMU because, again, the concrete masonry is going to be shrinking, moving away from the joint. So a little bit narrower joint's okay. If we're going looking at clay, clay really wants to be a little bit wider than that because you think about the clay is going to be expanding, it's going to be moving into the joint. So we want to have a little bit extra space in that situation. If I look at different reasons for putting in joints, so if we have a veneer, an unreinforced veneer, we put in different joints for different reasons, right? We have vertical joints that we use to prevent cracking. We have vertical joints that are needed when we have differential support conditions. If we have two different areas of the veneer that have different elements that are supporting them, we're typically going to put in a vertical joint so that we don't have a vertical crack that would occur. Very rarely would you ever eliminate a vertical joint. Horizontal joints are needed for differential movement, but not the same as differential support. Differential movement would be, say, the building structure behind moving differently than the veneer, especially for a clay veneer that might be expanding, but even for a concrete veneer that's really not going to have much movement at all. And the backup structure that it might be supported or tied to maybe wood, maybe studs of some kind that has differential movement. So having horizontal joints, shelf angles would be very common when we would have an unreinforced veneer tied back to structure. It's not to relieve the masonry material. Masonry is very, very strong. It doesn't need to be relieved, but you need horizontal joints in there because of some of the differential movement. And it should be noted, some cases they can be eliminated if we look at the differential movement and we understand the different types of veneer connectors that we might want to use. We can use veneer connectors that allow for more differential movement, and then hence you could eliminate some of the horizontal joints. So, just as an example, what differential support would be for those vertical joints, again, maybe an area of veneer supported by a foundation, and then an area of veneer that's supported by, say, a shelf angle that's tied back to structure. That would be a differential support. Differential movement, though, would be, say, a structure of some kind that could be shrinking, that could be moving in different ways, and a veneer that could be expanding, or even if it was a concrete veneer, really not moving much at all. And again, the structure behind it having some movement. So this would be an example for why we would want a horizontal joint for a building. So then, if I compared the what we had in there for um, all the architectural reasons, I would say for an unreinforced veneer, we had a bunch of different reasons. But then, if we looked at the reinforced structural masonry behind, so vertical joints, we'd still maybe add those to prevent cracking. We still might want to isolate the structural element. In some cases, vertical joints can be eliminated within a reinforced structural masonry design. So a little bit different than our veneer counterpart. Horizontal joints and a reinforced structural masonry, we just never need that. And so then you can kind of see that these are kind of separating pretty quickly. So when I say isolate an element, maybe we have partition walls or a non-load bearing wall connected to a shear wall or a load bearing wall situation. So different types of element, we maybe want to have a joint between them so that they can function separately and differently. So you can see this here in kind of an elevation where we maybe want to put some joints to isolate, say, a shear wall element. So one of the things that I do like to identify those, historically, maybe we used to put in a lot of joints in our shear walls, maybe to isolate these different elements, because it would be easier to analyze. So what we have is we have, if we have a building with a lot of openings within them, if we put joints at every openings, and I'm using this example to exaggerate a point, having a lot of tall, slender shear wall elements wouldn't be an effective use of material, but we maybe would have had to do this had we not had the proper tools for analysis and design. So it's too much isolation, it's too many joints, it's going to be way too much cost, but we're maybe doing this or we had done this in the past because of the simplification so that we could use um, typical maybe spreadsheet or hand calc tools for doing the analysis and design of a shear wall. But what we would like to see now is we would like to see longer walls. And the reason why we'd like to see this now versus later or before is because now we have software, we have several different programs that we can utilize to do a finite element analysis for this shear wall element. And so we still want to maybe put in some joints, maybe we want to isolate some elements relative to one another, but we don't need to put in all the different joints because we can have perforated shear walls within a finite element analysis program to have understand the overall behavior. So again, we typically want to have the joints located. So you can see in the previous example that if we had, all of those openings, we maybe would have quite a few of those openings with a still have a um, an actual movement joint or an expansion joint if it was clay at a lot of those opening locations. But like I just said, structural engineers, we want to eliminate a lot of those joints in that elevation. And so again, we want to make sure that architects and engineers are locating their joints separately on different documents. And if they're in the different location, then especially important that maybe we show elevations in both so that we can see where the differential is between uh, say, the veneer and the structure behind. And just a word of a caution, we do a lot of, here at Forest, we do a lot of project reviews and um, masonry reviews on a project, and a lot of times we still see designers locating movement joints with a single sentence in the notes or specification, and that's really not enough information for the mason. In fact, it actually leaves the door wide open for a mason to put in far too many joints, which is really going to adversely affect the overall structural performance. So, as structural designers, we really absolutely can't have any openings for more movement joints. We need to be very explicit and direct with where our joints go in our designs. So, is it true or false regarding the number of control joints and locations? To increase the flexibility of the wall, the more control joints that are added, the better. Um, so, it's going to increase the overall maybe flexibility of the system. It's going to make it weaker, but it's not going to make it a better overall design. So, I would certainly say false to that question. Because putting in additional joints really does change and affect the overall structural capacity. Control joints can affect the design, in plane and out of plane behavior. It certainly changes how lintels are able to operate within a wall. A lintel, we really want it to be connected to the wall elements on each side. In fact, we make a recommendation that there shouldn't be a movement joint or a control joint within 24 inches at least of the edge of the opening. If we put it any closer than that, I think we're really kind of affecting the ability for the wall to arch. So arching action is kind of an important part of lintel design, and that's obviously going to be very dependent on where you put your movement joints. For movement joints, we have a lot of different types of joints that we can use, and some of these are geographically just a little bit different, just because of how masons are used to working in certain areas. So, for instance, this preformed gasket being placed within, say, sash blocks with the actual joint in them to receive that preformed gasket, that's certainly pretty common in some parts of the Midwest. We can see a grout filled joint where we actually use building paper on one side, use kind of standard blocks for that overall wall construction, but then actually fill um, that space full of grout with a little bit of building paper so that it can move separately, but it does have a little bit of a keyway in there uh, to keep the walls in alignment with one another. Other options at the joint is to take any bond beam reinforcement and just put a smooth dowel, a dowel that maybe is bonded on one side and has is smooth or has a greased end on one side. So again, we have some ability to keep the walls in plane with one another, but not restrict any movement that it would have in plane or away from one another. So the overall impact on shear wall design is spacing the joints. Is obviously going to be critical. If you put the joints too close together, then the walls are just less effective. And the example that I like to make of this is if you have four 18-foot long walls, you're going to lose about 33% of the capacity compared to three 24-foot long walls. So the longer walls are going to be stiffer, going to be stronger, and using similar materials and reinforcement. That those four shorter walls are going to have less capacity and overall bending moment in plane for the wall. Now, the shear capacity of the walls is going to be equivalent. You have the same length of walls, but having longer walls has much more moment capacity and hence much more in plane shear wall capacity. But if you put those joints too far apart, say you went along that thought process and maybe just had two very long walls, two 36-foot long walls, then maybe they're just the joints would be too far apart. And then you'd have some thermal loading and you'd have some shrinkage, and then maybe would result in some cracking in the walls. So, a really close analysis, you really want to make sure that the joints aren't too close or too far apart for our overall design. And so here's what I'm talking about versus long walls versus short walls. The one extra joint in the top example is going to give up 33% of the overall capacity than if we just had the two interior joints, as you can see in the lower wall example. And here you can see some of the numbers that back it up. 8-inch block in both cases, F prime M of 2500, 20-foot tall wall, the one on the left having the three longer 24-foot walls, the one on the right having the four shorter 18-foot long walls, and then you can see the overall design capacity strength with the long walls having the 33% increase. There is a balance between, though, the horizontal reinforcement and the movement joints, kind of shown in this diagram that's shown in the CMHA Tech Guide 9-25. Also within that guide, it really does give us guidance for how to locate, amongst many other things. It's a long guide. It's got a lot of great information, but I'm going to really kind of boil it down to three kind of summary ways of having a balance between movement joints and horizontal reinforcement. So really kind of the first main option, which is what I would call kind of a typical standard option, is to put a minimal amount of horizontal reinforcement, and then which would be a 0.0007 area of steel to area of masonry. So put that minimal horizontal reinforcement ratio of reinforcement within the wall, and then have regularly spaced control joints. Given some guidance, it's 1.5 times the wall height, or as much as 25'4". And then there's some other limitations as well, but those are pretty standard type of limitations. And then the typical horizontal reinforcement would be horizontal joint reinforcement, or very very few bond beams with some horizontal rebar. So those would be kind of some minimal horizontal reinforcement examples. And then, like I said, control joints spaced pretty regularly. So the second option would be an increase in the amount of horizontal reinforcement, about 3 times the increase. So 0.002 from an area of steel to area of masonry ratio. And so that ratio should look pretty similar. It looks pretty similar to what we have within just a standard concrete wall, if you look within ACI code. And kind of using that same thought process, the big advantage to masonry is we just have a lot less continuous concrete. So in fact, if in a partially or ungrouted wall, we just have the face shells that would be continuous. So it's a relatively small volume of concrete that would be continuous. So we can use that smaller volume of concrete, use that reinforcement ratio, and place bond beams within a wall, say maximum 48 inches on center, and then really reduce or minimize the amount of control units that are going to be used in the design. And then we have a third option, kind of using that same thought process of 0.002 of area of steel to area of masonry for that reinforcement ratio. And then use a combination, though, of horizontal joint reinforcement, and then not too frequently used bond beams and rebar. So that really does allow us to increase the spacing between control joints, or really minimize them, and in some situations even eliminate them. Going back to that first option, really looking at kind of regularly spaced control joints, the guide also gives us some direction to what to do for joints at openings. So I point to this figure, point to this diagram, because really this is just meant for an unreinforced masonry design. I still see designers putting control joints at openings in a reinforced design. That's not recommended by the guide, and it's really kind of a poor building construction design practice to put a movement joint in a reinforced masonry wall at an opening. So again, the guide does say to put it there for an unreinforced masonry wall, which is why maybe in a veneer where we have an unreinforced veneer, that still makes some sense. The guide gives us some direction for what to do for a reinforced masonry wall. So when you have a reinforced masonry lintel, for instance, we have vertical reinforcement on each side, and we have sill reinforcement. we really have the amount of reinforcement that we need to prevent any cracks from mitigating from any corners. And really, this is what we should do for all openings within reinforced masonry walls. Move those moving joints away. If you could space them equally between openings, that would be great. But I would say at least 24 inches beyond the edge of the opening before I put a movement joint. So it would look something like this or that for our designs. So if we get to the second and third options that I talked about earlier, putting in an increase in amount of horizontal reinforcement so that we don't need to put in control joints, either with just reinforcement, bar reinforcement, or a combination of joint reinforcement and bar reinforcement. So we can achieve designs like the what you see on screen, where we can go, maybe 60, 80, 100 feet, depending on the amount of reinforcement, depending on the wall. This wall is going to be an interior wall, so that we were able to use and utilize a little bit more length in the overall design. So again, the different when I talk about reinforcement, what are some of the different types of reinforcement that we have? When I said reference horizontal joint reinforcement within a wall, the common joint reinforcement would be is 9 gauge wire. You also have a heavier 3/16 inch diameter wire option. So either one of those, and really the 3/16 inch wire is kind of a maximum reinforcement to use. The code says to not put reinforcement within the mortar joint that's more than half of the 3/8 inch in common mortar joint, hence the 3/16 inch wire that is allowed. And I would just say that for masons that work with these materials, having using that maximum is should be something that would be rare for the special circumstances when you really, really need it. We'll talk about what types of reinforcement you actually need, and I would just recommend to engineers to not use that heavier 3/16 inch diameter wire unless they absolutely need it for a particular reason. So again, you have those two joint reinforcements. Then you also have the bar reinforcement, which is going to be your standard again, number 3, 4, 5, 6, maybe number sevens, eights, and nines. But again, using the larger bars pretty sparingly. So how much wear? There's kind of a couple different methods that we can reference within those guides. The code doesn't give us a lot of direction on how much horizontal reinforcement to use, but again, we've been referencing that CMHA Tech Guide 9-25 that really does give us some pretty good direction on horizontal reinforcement. Table 1 within the guide under the empirical method would give us, again, that 1.5 uh, height to length ratio. So again, go ahead and utilize that if you'd like, and then you can see a maximum control joint spacing, 25 foot 4 for standard 8 inch high units, or if you had a 4 inch high units, maybe just 20 feet, or concrete masonry veneers to be 20 feet as well. Again, within that same empirical method, then you can see the different size reinforcement to use and then the maximum spacing that would be used. And again, this is the empirical method. This is going to be based on a lot of different um, designs and reviewing a lot of different constructed projects and what's worked so far in the overall design. If I switch to the engineered method, so really kind of empirical is going to be based on built construction. Engineered method is really kind of looking at a little bit closer look of the materials, the reinforcement that you could use, kind of looking at that reinforcement ratio of 0.0007. So kind of still that reduced reinforcement ratio. But what I think is interesting is if you look at this and you look at some of the reinforcement that you would have in here, for the partially grouted walls, it matches pretty close to what the empirical method would have showed for the amount of reinforcement. For example, if you look at the far right column in this table, you can see that for most walls, the two 9 gauge wires, 16 inches on center, would be more than sufficient for that design. If you go to fully grouted walls, though, you can see, well, wait, in fully grouted walls, I have a lot more continuous concrete. I'm filling up the voids with grout. So then in that situation, I would actually need a lot more horizontal reinforcement for a fully grouted wall. So engineered method, really kind of looking at the actual materials a little bit more directly to try to anticipate what the amount of reinforcement wire would need to be in these designs. So again, we take it a step further, still staying within the engineered method, but now looking at the amount of uh, horizontal reinforcement that you can utilize. And again, looking at the steel reinforcement and the concrete material and how the two materials relate to one another. This is the amount of reinforcement that you would use to prevent any cracks from opening in the design. So really, this is focused on trying to make sure that we have enough reinforcement to prevent any cracks from um, cracks are always going to occur if it's concrete masonry, if it's concrete in general. We know that it cracks. This is the amount of reinforcement that you would need to really keep those cracks closed, so that you don't have any potential um, aesthetic issues or any other issues with the wall. So again, this balance of reinforcement again is also pretty close to what you'd see within the concrete ACI code. So you can see the reinforcement that you would use in these situations. So this table within the tech guide is going to give us the bar reinforcement that you would need to use within bond beams. And again, bond beams not spaced more than 48 inches on center. So again, using all the thought process of what was put into those tables, what I did in this design table is actually expanded different reinforcement options and actually looking at using joint reinforcement in addition to the standard bar reinforcement that's in the table. So we have very good uh, correlation between the tables that are in the guide and the one that we created. So this is again just looking at all of that reinforcement that would be needed. And then what we did, we made a second table for combining. On the far right side, you can see a column that has joint reinforcement at 16 inches on center. Why create this table? Well, what we found was a lot of designers and a lot of contractors were working within areas where maybe they had a cavity wall, and the cavity wall used kind of an iron pintle support system for the veneer, and that required um, joint reinforcement. So within the joint reinforcement that was already there, if I utilize that reinforcement plus the bar reinforcement that you can see in the table, you can see the combination of the two is what will give us the reinforcement for, again, that 0.002 steel to concrete masonry ratio. So again, a little bit look at the same information with a couple different tables that we've expanded for design. So control joints and masonry lintels, obviously masonry lintels within all the different coalitions that we work and all the different designs that we do, we're very big advocates for masonry lintels, mainly because they're more effective for an overall structural design. They actually cost a lot less. They're going to perform and function within the building a lot better than using any other form of material within a masonry wall. So we know that masonry lintels are the best option for the design for both short and longer walls. Masonry lintels are going to be the best option within a building. And where those control joints go, if they're away from the openings, here at least you can see 24 inches beyond the edge of the open. We know that the lintel then can be more of an integral element to the jams and the overall wall system that we're designing. Really putting those openings in the wall with those lintels and control joints moved away, we really need to have a finite element analysis tool to have a good understanding for how the different forces are going to be operating within this wall. And again, so moving those control joints away does kind of demand us to have a little bit better tools for the overall analysis and design of these elements as well. So you're going to see here within the area of the lintel above the opening, you can see some positive and negative moments that are occurring in the overall design. Again, as long as we're getting those control joints away, we can see that those lintels can have continuity with those jam elements. So again, here making sure that in this details, we have that control joint located 24 inches past the edge of the opening or further to the right. Kind of the same for the elevation. So again, we can show it here in elevation, showing those control joints that want to be away. So when they're away, you can see the forces are able to move, flow around the opening, but not if I put that joint at the edge of the opening. It really needs to be away so that you can see they have that thrust load that can be uh, then horizontally shed into the jamb or to the wall adjacent to the opening. So this kind of gives us some different strategies and options to look at. If I asked a bunch of different contractors what they would prefer using control joints at 25 feet in center, so kind of the standard option with the standard joint reinforcement at 16 inches on center. So that would probably A is going to be probably the most common option that's used today, or B, again that same control joint spacing, but now use bond beams instead of horizontal joint reinforcement. C would be eliminating those joints using the amount of reinforcement that you would need in just joint reinforcement. D would be no control joints, um, no joint reinforcement, but two bond beams. Um, or then number E, where you'd have no control joints, no joint reinforcement, but bond beams very regularly spaced at no more than 4 feet on center. So all those different options kind of give us the same overall design capacity and results. So option A, option B, pretty similar to A, but with no joint reinforcement, just bond beams. C is going to be the no control joints, but then much further spacing, or much further spacing to the control joints, but a lot more horizontal joint reinforcement, or joint reinforcement plus bond beams, or just bond beams. So you can see A through E, all the different options. If I start to introduce openings, that also adds in a little complication. Add in openings plus give that 24-inch space between the edge of the opening and control joint, really kind of seeing, joints popping up kind of all over the place. Or D, again, with the openings, lintel reinforcement, joint reinforcement, and really kind of a long spanning wall without control joints. So you can see what contractors preferred was either A, where we can just use the joint reinforcement. So it makes sense that that would be the most typical option today. We still have some contractors that if you don't need joint reinforcement, they'd still be glad to put in some bond beams. So A was going to be the most preferred option. But then D also was the preferred option once we landed with a lot of openings within a wall. So having no control joints in that elevation, no joint reinforcement, but then just a couple bond beams, at the lintel and sill location. So becoming more and more popular, especially walls with more openings. So speaking of that, looking at some case studies that we looked at with these elevations where we maybe have piers that would be difficult to locate movement joints. So that was planned. Here you can see the elevation view. What we're recommending in those designs is to see that horizontal reinforcement in your lintel and at your roof bearing location and at your top of wall, in addition to the joint reinforcement that you would have in there, would allow us to move those movement joints beyond these areas with a lot of openings. Now, maybe for the rest of the building, you go back to the standard control joint layout every 25 feet or 1.5 times the wall height for the regular control joint. So we have a couple different options. So we can design one area of the building without joints and then resume the standard practice for the rest of the building. Really, when I look at a design like this, obviously there's a lot of problem areas. We have, first of all, we just have too much isolation. We have an elevation that really doesn't have a lot of in-plane shear capacity or vertical load bearing capacity. We really diminish that capacity by having to put in those joints. Now, those joints had to be in there because of the steel that we have within the wall. The steel is going to be moving differentially than the masonry, which really does drive the demand for those joints. But then that really does diminish the overall wall capacity versus a masonry lintel, masonry elevation. We're able to eliminate the joints in this elevation where it's going to have a lot more capacity in design. So just doing a kind of a really quick um, animated shapes between the two. You can see the image at the bottom. You can see a lot higher stresses, a lot, sharper colors, we'll call them. The dark blue, dark red, you can see the higher stress concentrations when we have these two different elevations that face same amount of load. So the one on the bottom is going to have higher stresses, higher forces, and more deflection. The one at the top is going to be acting more like a moment frame, less stress, less force, better flow between horizontal and vertical elements. So here's an example with some um, perforated shear walls. Even doesn't have to be dock doors, could be just windows within the elevation. Here you can see another example where we have an elevation that we have a change of height of wall, some long span openings, some short span openings. Again, taking some of the lintel reinforcement, making it continuous, eliminate some control joints from places that we don't need it because of the horizontal reinforcement. Kind of that balance between the two really does work out well. So then a similar elevation on the same building. Sometimes we still want to put in those movement joints. So again, if we have differential support or we have differential use of the wall, maybe we want to put in some control joints in some of those locations, but then move them out past these areas of repetitive openings. And then a little tidbit here on, when we have shaft walls are excellent elements for resisting both load bearing and shear loads for a building. When we look at those shaft walls and keep all of the walls together as a tube style element, it's going to have a lot more capacity. If I would introduce joints into those shaft walls, though, what I do is I reduce the overall capacity. So just a really quick tip is don't put movement joints there. Make sure that we have enough horizontal reinforcement to not have any joints within these shaft walls, within these tubes, vertical tubes within a building, and then we'll have a lot more capacity. When I have the joints, it really does basically break the walls into two separate groups. And we all know as engineers that tubes are going to be a lot stronger than individual plate elements. And so for the very same reason, a shaft wall is going to be a lot stronger if we keep it together as a box, tubed like shape, and not have the individual plate elements. In fact, a lot of these examples that I've looked at, you have somewhat on the order of twice the capacity for a shaft wall that has no joints versus a shaft wall with joints, where you'd have a lot more limited capacity. Here you're going to see just a really quick analysis and deflected shape of the different plate elements. And again, look, using finite element analysis really does help us with a lot of these types of designs. So what options are available for control joint placement and horizontal reinforcement? Regularly spaced control joints and standard horizontal joint reinforcement, regularly spaced control joints and horizontal bond beams with reinforcement, or increased horizontal reinforcement and no control joints, or all of the above. And of course, it's all of the above. We do have a lot of different options within movement joints and horizontal reinforcement. For our buildings, we do have different options for different scenarios that we can use for our designs. So, in conclusion, again, we have these different options for horizontal reinforcement, movement, joints, purpose, and locations. We have a lot of different options that we have there. Um, so, we understood all of that stuff. We've learned about the different reinforcement and movement joint strategies. And then we definitely discussed some of the different design impacts of various options within our designs. So, a lot of different resources that we can utilize for some of the things that we discussed in this presentation. So, with that, I thank you very much. And then just a few more things here, some commonly asked questions. If we use bond beam reinforcement options, do we still need joint reinforcement? And really, you don't. Either solution can be sufficient, but both that joint reinforcement and bond beams, neither one are required, but utilizing both together, I think, is a really good option for minimizing those joints and having a good distribution of reinforcement in an elevation. So if we use the engineered method where we can eliminate those joints, um, does that mean that you really don't put any joints within a building? And I would say there's still reasons to put in joints, even if you don't need to have it for some of that crack control. Just because the overall length of buildings, if you had a 200-foot long building, The thermal loads for a 200-foot long building would actually make the building grow, increase in length or shrink, somewhere in the order of an inch to inch and a half. And do you actually have the ability to have that much movement without having the building have other problems from the wall to the base, or from a wall to an adjacent building, or other structural elements that you have? So you still maybe want to add in some joints to just break down some of the thermal loading that you would have in the overall design, different support conditions, change of wall height, all different things that you want to certainly consider when putting in joints. And then another question, if it really goes from 25 feet with one scenario to infinity, is there some length in between that you can utilize? And certainly, I think that there's some reasoning behind it. There's just not a lot of data to support, some intermediate range of reinforcement. So if you go from 0.0007 at 25 feet and you go to 0.002, and then you don't need any, so between 25 feet and infinity, definitely there would be an intermediate location, but there's just not a lot of data to support those other options in design. All right, so that would go ahead and wrap us up for today. If you do have any questions, you can always reach out to me at sam@forceconsulting.com. Thank you very much.